So we're going to finish up 9.1. The last thing we have to talk about here is permutations. The permutation is a special case of the fundamental counting theorem. And what it involves is taking a large set, your sample space, and breaking it up into a smaller group where within that group order matters. And you'll see that'll become more clear in a second when we do some examples. Biggest thing to remember, we use the notation what we call NPR. N means your total, your sample space. P stands for permutation. And R stands for the people that are going to be in this smaller group that we're putting in order. Or that couldn't just be people, it could be, you know, marbles or cards or whatever element we're talking about. So let's see, before we do this, let me show you a little bit more what I mean. Let's say we have our class here, our 9 people in our class, right? What we'd use a permutation for is I'd say, okay, with these 9 people we have here today, I want to order you in different ways. I want to put you in order. So let's have 3 for you guys. You guys stand up. You 3. Of the 9 people, come on, get up. You 3. So of these 9 people, that was my sample space, right? I'm going to take these 3 and I'm going to put them in an order. So here's one order they're in right here. So you switch. This is a second order that I put them in. Now I could switch. I could have one of them sit down. I could have you stand up. One of you sit down. Now I still have 3 in another order. Now two more people could switch. There's another order. All these are different permutations. And what the total number of these orders I create, if I made every one of you stand up and switch, is what we get when we do a permutation. All right, you guys can sit down. The way we do it, we plug it into this formula, n factorial over n minus r factorial. You guys remember factorials? What is a factorial? Nobody remembers? Yeah, so if I had like 5 factorial, what would I do? 5 times 4 times 3, 2. You start at this number and you're multiplying down to 1. Now you're going to have, I think, 1 or 2 problems where you're going to have to use this formula out. Most of the time, though, we're going to be able to just plug in the NPR into our calculator, and it'll give us the answer we're looking for. So let's give it a shot here. Let's say I have 5p2. What does 5p2 mean? What am I doing? Remember what I do here with the class. I took the 9 of you and I split you up into groups of 3 in order, right? What does this mean? Yep. Not just groups of 2, though. Groups of 2 where order matters. That's the big key to permutations. Order matters. If I switch you 2 around, that's 2 different things. So to calculate 5p2, you're going to add a calculator page, and you're going to look right here in menu, probability, and where it says permutations. It's going to give you NPR. And then you just plug it in. In our example here, N was 5. Remember, it's NPR. N was 5. R was 2. N was 5. R is 2. There are 20 different ways to order that group. Okay? Now, as a side note, can N ever be smaller than R? Can my first number ever be smaller than my second number? Why? What does N represent? Yeah. Yeah. And what is R? Yeah. So can I ever order more people than I have? Can I split you 9 people up into groups of 10? No. So n is always the bigger number. Keep that straight when you're punching your calculator. Give these two a shot, 10p2 and 10p10. Come on. Oh, is that the only one? That is the only one. I forgot the next one's on here. All right. Jump over to 9.2. Jump over to 9.2. And we got, remember, this is your formula. Order matters with permutations. Everybody give this one a shot. School's having tryouts for 8 parts in a play. 15 students are going to audition. How many different casts can be made? Remember, we jumped over to 9.2 now. All right. What are we going to use for this one? Yep, permutation. 15p8. Now, here's a question. Why does order matter here? Because this is something you're going to have to identify in a second. Why does order matter? From the question. I can't have less than, yeah. But in other words, why does it matter that if I am guy Steve in the play, is that that's different than if I'm John? Why does that makes a difference, right? No other way to describe it. But in other words, you're going to figure out, does the order actually matter? So in this case, it does. 15 people, 8, what do we get? Yes? Yes. A lot of different casts we can make. So now we looked at permutations. Let's take a look at combinations. This is where it starts to get a little bit more interesting. A combination is another special case of the fundamental counting theorem. What it is they're used when you're taking a set, just like before, and you're splitting it up into a smaller group. But here, they're unordered, the smaller group. So here, I'll do the same example. We have the class of 9, right? You 3 stand up again. Here's one order. If I had 2 of them switch, now I'm saying they're the same order. It's still only 1, whereas before, now we had a different order. In a combination, this is the same thing. But if I had, Gabby, stand up again. One of you, who sat down last time? Yeah, you sat down last time. These 3, now I have 2, this is my second one. If I have them switched, it's still the second one. It's the same. Right? Thank you. Formula we're going to use is right here, just like permutations, notated pretty much the same way, except with a C, NCR. N is still going to mean our sample space, our total number. R is still going to mean the number of things that we're ordering, combination. In the formula, once again, I think there'll be a couple questions where you're going to have to use a formula, but most of them will be in your calculator. The only difference is this extra R factorial in the denominator. That makes sense, right? We have less, now we have less orders, right? We're going to make it smaller by dividing 1. All right. So you'll see the difference in this example now. Let's say I have 15 people on my team, and I need to pick 7 to start my Frisbee game. Okay? Does order matter this time? Does it matter if you get picked first or if you get picked seventh? No, only emotionally. It's the same team I'm going to form, regardless. So that means we're going to use combination, not permutation. How do you set up the rest, though? How would you set it up? 15C7. So again, same thing with combinations. Also, make sure your n is always bigger than your r. 15C7. To calculate these, it's pretty much the same place. You're going to go to a calculator page, menu probability, except this time combination, not permutation. And then you just type in the same thing, 15C7, 15 comma 7, right? 6,435 different starting lineups that I can make. Okay. Which number is going to be bigger, the combination or the permutation, if I have the same thing? Permutation. Why is permutation going to be bigger? Yeah, I got a lot more permutations than combinations. All right. Take a look at this example. What's going on here? It's something we haven't really seen before in the rest of these. I got a bag with five red marbles and 7 blue marbles. How many ways are there to get 2 red and 4 blue? What's different about this now? Versus that other one, where I just had 15 people and I chose 7. It's two different things, 2 different categories, call them. Can I do it in one combination if I have 2 different categories? No. I got to break it up. Here's the other question. Now you have to ask yourself, does it matter if I pull out red marble 1 and then red marble 2, or red marble 2 and then red marble 1? No, so what are we going to use? Combination. What will be my first combination? 5C2. I have 5 red marbles, and I want to choose 2 of them. What do I want from my other combination? 7C4, how come? Excellent. Okay, what am I going to do with these 2 combinations? Somebody from this table, you guys are all too quiet. You gotta wake up. What do I want to do with these combinations, do you think? Remember, the combination is a special case of the fundamental counting theorem, right? What did I do in the fundamental counting theorem? What did I do with the numbers in the fundamental counting theorem? Multiply. What do you think I do here? What do I do here? Multiply. You multiply 2 combinations together to get your answer. Anytime you're breaking up the event into smaller events, you multiply them together. The rules for the fundamental counting theorem don't go away in a special case. So here, I'll put it on this calculator. You can type it in just exactly how you'd like to. The first combination, 5C2. Make sure you watch your parenthesis and multiply by 7C4. Oh. Everybody get 350? 350 different ways I can pull out the marbles. So in that example, what did we count? Let's say we're asking the probability of pulling out marbles. Did I count my total ways, or did I count my favorable outcomes? Favorable outcomes. My total ways are just pulling out 6 marbles somehow. My favorable outcomes were I specifically got 2 red and I got 4 blue. That was our favorable for that circumstance. I know it's not a probability question, so it's a little fuzzy, but yeah. So now we've learned these methods for counting. What were they? What was the first one? What was the most basic one? A basic counting method that we learned last class. What was it called? The fundamental. When do we use the fundamental? Does anybody remember? Can anybody describe those problems we use the fundamental on? Anybody remember? What happened in those problems? Like we had the lunches, right? We had ways to get a lunch, and we had 4 different pizzas and 2 different sodas and 3 different fries or something. What happened there? We did multiply, but what happened with the event? The event of choosing a lunch. We didn't just choose a lunch, right? We broke it up. We broke up the event. We took the event of choosing a lunch and we broke it down into choosing a pizza, choosing a soda, and choosing a fry. All right. What was the next counting method? We started it today. Permutations. Permutations. When do we use permutations? Specifically when? When we care about the order. Order matters. Whenever order matters, we immediately start thinking about permutations. What about the last one? Combination. When do we use combinations? Order doesn't matter. So what we can do is sometimes we're not told we're going to use combination, we're going to use permutation, we're going to use this. We have to figure it out on our own based on the information in the problem. So take a look for here. 4 people are going to be chosen for a relay team from the 25 people on a track team. How many different teams can be formed? What do you think I'm going to... How come combination? Still all on the same team, right? So how did I set up my combination? 25C4, perfect. 25 people in my group, I'm going to choose 4 of them. What do we get? $12,650. 12,650 different teams I can make. All right. Everybody give this one a shot on your own. For 5 different, if you're going to have 5 different schools in the race, and we want to know how many different orders of finishes there are for the top 3 places. All right. Do it on your own, and then write down why you chose the method you did. 3 methods to choose from. Write down which method you used and why. Or type it, doesn't matter to me. Was it? 60. The order matters in the finish of a race, so we use permutation. Yeah. Yep. Remember, permutation is a special case of the fundamental theorem. How'd you set up your fundamental theorem? 3 finishers. We could have 5 here, we could have 4 here, and we could have 3 here. Exactly. It would. But that's a lot more work, and there's a lot more places for error there than there are just pulling 2 numbers off and putting them in a permutation, right? So you can do that. It's not that you're wrong, but this is definitely much better. And sometimes they might ask you to set up on the multiple choice. They might say, how would I express the ways for this? And they won't give you the number answers. They'll say like 5p3. They might put 3p5. They might put, and you'd have to choose the permutation. But you could use this. And if you don't know, in general, the fundamental theorem is another way of doing it, but it's more long, it's more drawn out. It's better if you can identify that it's a permutation and do that. All right. Let's try one more here. At the track meet, the committee must decide which metal design to use. 4 possibilities for gold, 3 possibilities for silver, 2 for bronze, or 4 for bronze. How many different possibilities are there? Do the same thing. Find the answer and write down why you chose the method that you chose to find the answer. All right. What method does somebody think? Fundamental. Why do you want to use the fundamental here? Separate events that we broke down a big event of choosing a metal. We had choosing a metal. That's our event. We broke it down into gold, silver, and bronze. So how'd you set up your fundamental theorem? So you had 3 blanks. You said there's 4 possibilities for gold, 3 for silver, and 4 for bronze. What'd you do with these numbers? Multiply them together, and we get 48. Now here, don't think there would have been an alternate method to use. Anybody use something different besides the fundamental? All right. We are not going to go on to that. I got a couple minutes left. Your homework for tonight is pages 3 through 5 in the packet. And what I want everybody to do, you can finish it. You should have time, might have time to finish before you leave. Try to find number number 5 on page 3 and number 4 on page 4. Do those really quick right now. It shouldn't be much more than your calculator. So that's, remember, we have a review class tomorrow night, and we won't be after school tonight.